Right at this moment, as you are listening, something unprecedented is happening. In our solar system, ever since Comet Atlas was discovered in July, things have been getting stranger by the day. This ancient visitor from between the stars has puzzled astronomers from the very first day, but its strange chemical composition and its characteristic green glow are no longer the strangest thing about it. The strangest thing is what has followed. In its orbit, our usually quiet and predictable region of space has turned into a bustling highway of gathering celestial bodies in patterns that defy all laws of probability. From a swarm of 7 comets appearing at once to a new wave of asteroids flying close to Earth, what we are witnessing in the night sky is anything but normal. And now, astronomers are wondering how Comet Atlas is truly impacting our solar system. Join me tonight as we explore to find out whether we are witnessing the galaxy's greatest coincidence or a phenomenon that is much more profound. Part 1. An approaching wave of asteroids. Mid-September 2025 should have been a quiet month, just another month of routine cosmic traffic, the kind that astronomers log with mechanical precision, before moving on to the next observation. But the universe had other plans. What unfolded during those crisp autumn weeks was anything but ordinary. A celestial parade had scientists scrambling to their telescopes, and the public wondering if we were witnessing something more than random chance. The first headliner to appear was Asteroid 2025 FA22, a colossal rock measuring 130 to 290 meters in diameter. On the 18th of September, it skimmed past Earth at just over 2 lunar distances, about 835,000 kilometers away. Close enough to make headlines, far enough for us to sleep soundly. But this is where the story gets interesting. FA22 did not arrive alone. This was not a typical solitary asteroid making a scheduled appearance. Instead, it was like the opening night of a cosmic theater, with more actors taking the stage one by one. The smaller, near-Earth object, 2025, Raji, had appeared 3 days earlier on September 15th, flying past at just 0.78 times the lunar distance, which is only 300,000 kilometers from us. In astronomical terms, that was almost a handshake. But these events were not isolated incidents. Throughout that week, dozens of visitors at satellite distances traced their orbits through our local neighborhood, each one cataloged and tracked by the global network of space surveillance systems, which, by the numbers, was typical traffic. However, there was something unusual about this concentration. The timing seemed orchestrated, as if these ancient travelers had coordinated their appearances for maximum dramatic effect. Then came the supporting cast. Comet C 2023 P1, discovered by the SWAN instrument on the SOHO spacecraft on September 11th, began to brighten to naked eye visibility near the constellation Virgo, its tail stretching across the dark sky, like a visible cosmic brushstroke to anyone who knew to look in the right direction. As twilight gave way to darkness, the comet's fate after perihelion remained uncertain. Many such objects disintegrate under the intense heat of the sun, leaving only glowing trails of debris as monuments to their brief existence. Meanwhile, lurking in the background of every astronomical bulletin was another familiar face, Apophis, officially designated 99,942 Apophis. This was the asteroid that once topped every planetary defense concern. This 400-meter rock is projected to make an uncomfortably close approach to Earth on April 13, 2029. That flyby will bring Apophis within 32,000 kilometers of the planet's surface, closer than our geostationary satellites, close enough to be visible to the naked eye, as it streaks across the night sky at 50 kilometers per second. But the real star of this celestial show was still waiting, hidden among the discovery announcements. It was something unprecedented from Atlas. also known as C2023A5, a new #1 priority object. It was discovered on July 1st, 2025 by the Atlas survey team in Chile. This object was different from everything else that occupied our telescopes that September. It was not just an asteroid or a comet from our local solar system family. This was something far more peculiar, an interstellar visitor. Only the third confirmed object to carry the chemical signatures that would challenge everything we thought we knew about planetary formation. The Atlas team initially detected it as just another faint dot moving against the background of stars. But as subsequent observations refined its trajectory, the mathematics told an extraordinary story. This object was traveling on a hyperbolic trajectory, meaning it possessed enough velocity to escape the sun's gravity entirely. It had come from somewhere else, another star system, perhaps many light-years away, and after its brief encounter with our neighborhood, it would continue its journey into the cosmic dark, never to return. What made the Atlas object even more remarkable was its timing. Its projected perihelion was on February 15th, 2025, just a few weeks after the September asteroid parade. Then, like a performer exiting stage left, it would disappear into the sun's glare, obscured by the star's overwhelming brilliance. But patience would be rewarded. In early December, as Earth's orbital motion carries us to a better vantage point, the Atlas object would re-emerge from behind the sun's curtain, offering telescopes their best chance to study a true specimen of an interstellar object. The viewing window was perfect. Too perfect, some might say. At its closest approach in December, the object would still be 1.88 astronomical units from Earth, equivalent to about 270 million kilometers, far enough away to pose no threat, yet close enough for detailed spectroscopic analysis by our most powerful instruments, as if the universe had sent a carefully packaged sample from another star system directly to our astronomical doorstep, complete with optimal viewing conditions and ample time for study. But why now? Why this sudden flurry of cosmic activity, concentrated around these same few weeks? Better surveys certainly played a role. The Vera C. Rubin Observatory had just captured its first light images in June of 2025, netting thousands of new asteroid discoveries in just 10 hours of operation. More eyes were scanning the skies with greater sensitivity than ever before, revealing the true population density of small bodies in our solar system. However, the timing seemed too convenient, too orchestrated to be dismissed as mere observational bias. Was there something special about September 2025? Some gravitational convergence or some seasonal alignment that drew these objects together? Or were we witnessing the beginning of something larger, a cosmic drama unfolding on a timescale far beyond human perception? The mood among astronomers was not one of fear, but of urgent curiosity. Planetary defense systems had evolved significantly since the days when impacts were merely the stuff of disaster movies. Now we had the technological capability to track, characterize, and even deflect potentially hazardous objects. The recent success of NASA's DART mission had demonstrated that kinetic impactors could successfully alter an asteroid's trajectory, while the European Space Agency's Hera mission was on its way to forensically examine the results. But knowledge and preparation are only as valuable as the warning time available, and that raised uncomfortable questions about the visitors we had not yet seen, those still approaching from the direction of the sun, hidden in its glare until the final approach. If FA-22 had been on a collision course instead of a safe flyby, would we have had enough time to mount an effective response? And Atlas, with its alien chemistry and interstellar origins, what did it tell us about the population of unseen objects drifting between the stars? The September surge had awakened something in the collective consciousness. It was not panic. It was a realization that Our solar system was far more active, more connected to the wider galaxy than we had ever imagined. We were witnessing the prelude to humanity's transition from a species that lives on a planet to active participants in galactic-scale phenomena. But first, we needed to understand what we were facing. If FA-22 had hit Earth instead of flying safely past, what would that impact have looked like? Part 2 delves into FA-22. What would happen if an impact occurred? The mathematics of cosmic collisions are harsh as asteroid 2025 FA-22 grazes past Earth. On September 18th, at a distance of 835 kilometers, it carries kinetic energy, equivalent to about 100 megatons of TNT. To put that into perspective, that power is about twice the bomb that flattened Hiroshima, all concentrated in a single rock, with a diameter of 130 to 290 meters. But energy is only part of the story. What matters most is how that energy is delivered to our planet's surface, and that depends entirely on a complex physical dance, involving the atmospheric entry angle, the object's composition, and even the random luck of the cosmos. The difference between a regional catastrophe and a global extinction event often depends on simple factors, such as whether the impactor is made of solid iron or loose rubble. It arrives at a steep angle or just skims the atmosphere, and whether it explodes in the air or penetrates to the ground. FA-22's approach velocity of about 18 kilometers per second is typical for near-Earth objects, fast enough to compress and heat the atmosphere in front of it into a shell of plasma, but not so extreme as to suggest an origin from the outer solar system or beyond. At that speed, atmospheric entry would be incredibly violent. The object would begin to glow like a second sun, while still hundreds of kilometers from the surface. Its leading edge would reach temperatures of several thousand degrees as it plows through ever denser layers of air. For a rocky asteroid the size of FA-22, the most likely scenario is an airburst, a complete atmospheric detonation occurring at an altitude of 5 to 15 kilometers above the surface. This is what happened over Tunguska, Siberia in 1908, when an estimated 3 to 15 megaton airburst flattened over 2 square kilometers of forest without creating a crater. The FA-22 event would be significantly more powerful. Imagine standing 200 kilometers from the epicenter. On a clear morning, first would come the light, a flash brighter than the sun, visible even in broad daylight, searing retinas and igniting clothing and vegetation over hundreds of square kilometers. The thermal pulse would last for several seconds, long enough to cause third-degree burns on exposed skin. At distances beyond 100 kilometers, then comes the sound. The shock wave from a 100 megaton airburst would shatter windows over an area the size of a small country. The pressure wave would flatten most buildings at the epicenter and cause significant structural damage at a distance of nearly 150 kilometers. Even well-built concrete structures would suffer heavy damage within the inner destruction zone. But what if FA-22 were made of a denser material, or came in at a shallower angle, allowing it to penetrate deeper into the atmosphere before breaking apart? The crater scenario presents a completely different kind of destruction, using established impact simulation programs. Like Impact Earth, we can estimate that an iron asteroid, 200 meters in diameter, impacting at a speed of 10 kilometers per second, would create a crater about 3 kilometers in diameter and 500 meters deep. The immediate effects would be apocalyptic for anyone within sight. The impact would vaporize the asteroid and an equivalent mass from the target, launching millions of tons of superheated debris on ballistic trajectories. It would rain down incandescent material over thousands of square kilometers. The seismic shock would register as a magnitude 6.5 to 10 earthquake, collapsing buildings and causing landslides over an area hundreds of kilometers wide. However, perhaps the most terrifying scenario would be an ocean impact. Over 70% of the Earth's surface is covered by water, making this the most likely outcome for any randomly incoming asteroid. When cosmic objects strike the ocean, they don't simply vanish into the depths. With just a big splash, they create something far more dangerous, a tsunami. The physics of impact-generated tsunamis is still being refined by researchers, but recent models suggest that even an asteroid 250 meters wide, striking the deep ocean, would generate initial waves over 100 meters high. From the impact site, these waves would propagate outward at the speed of a jet airliner, carrying enough energy to remain dangerous across entire ocean basins. An impact the size of FA-22 in the middle of the Atlantic Ocean could generate 10-meter-high waves, making landfall on coastal cities from Boston to Barcelona just hours after impact. However, there is an important caveat often overlooked. In disaster scenarios, wave height decays with distance. Classic hydrodynamic simulations show that tsunamis lose energy as they travel, with their height typically decreasing according to predictable mathematical laws. A 100-meter-high tsunami at the impact site could diminish to 10 meters by the time it travels 60 kilometers, and continue to decrease as it crosses the ocean basins. The problem, as always, lies in the details of coastal geography and local depths. The question of regional versus global impact is crucial to understanding the true threat posed by city-killer-sized asteroids. An impact from FA-22 would certainly cause regional devastation, potentially affecting millions of people, but it would be unlikely to trigger global climatic effects or threaten the entirety of human civilization. That level of destruction requires much larger impactors, those measuring 1 kilometer or more in size, and which impact perhaps once every few 100,000 years. For comparison, consider the Chelyabinsk event of February 15, 2013. That 20-meter diameter meteoroid created an airburst equivalent to about 500 kilotons of TNT, injuring over 1,500 people, mostly from flying glass from shattered windows, and providing the world with dramatic dashcam footage of what happens when cosmic debris collides with modern civilization. The Chelyabinsk object was only about 1/10 the diameter of FA-22, illustrating the extent to which impact energy scales rapidly with size. What made Chelyabinsk particularly alarming to planetary defense experts was not the damage it caused, but the fact that it arrived completely undetected. The asteroid approached from the direction of the sun, hidden in its glare until the final moments. Before entering the atmosphere, no Earth-based telescope saw it coming. This represents one of the fundamental blind spots in our current detection network. The sunward approach corridor remains a region where even city-sized objects can arrive, with almost no warning. The safe flyby of FA-22 actually provided valuable real-world experience for international planetary defense coordination. The asteroid's brief appearance on the risk assessment list of the European Space Agency, followed by its removal, after additional observations refined the trajectory, gave agencies practice in the delicate art of public communication about potentially hazardous objects. How do you inform the public about a potential threat without causing a panic? How do you coordinate international response efforts when dealing with objects that could affect multiple nations? The International Asteroid Warning Network conducted a practical exercise during the approach of FA-22, testing communication protocols and observation coordination procedures, which would be essential in a real emergency. While it ultimately turned out to be a false alarm, this did not diminish the value of the experience. In fact, it provided something even more valuable, proof that the system could function under pressure. But the exercise also highlighted serious vulnerabilities that still exist in our planetary defense capabilities. Lead time is everything when it comes to deflecting an asteroid. The earlier we detect an object that is potentially hazardous, the smaller the deflection required to safely alter its trajectory. A gentle nudge years in advance can eliminate the need for drastic, last-minute measures. Current deflection technology, as validated by NASA's successful DART mission, relies primarily on kinetic impactors, essentially playing cosmic billiards with asteroids using high-speed spacecraft. This technique is effective, but it requires precise knowledge of the target's composition, structure, and rotational state. A rubble pile asteroid responds very differently to an impact compared to a solid iron mountain, and a miscalculation could mean the difference between a successful deflection and a catastrophic fragmentation. The FA-22 scenario serves as a sobering reminder that we live on a planet situated in a cosmic shooting gallery. Most of these are harmless particles, the size of sand grains, burning up harmlessly in our atmosphere as meteor showers. But occasionally something larger slips through the cracks in our detection network, and when that happens, the consequences can be devastating on a scale ranging from neighborhoods to entire civilizations. The good news is that we are getting better and better at watching this cosmic neighborhood. New surveys and telescopes are coming online with unprecedented capabilities to detect and track potentially hazardous objects, while infrared observatories, the void in detection from the sun's direction, would soon be filled, allowing celestial bodies to arrive unannounced. However, as we became more proficient in cataloging threats in our local neighborhood of our solar system, we also began to realize that we still knew little about the wider cosmic environment, as objects like Oumuamua reminded us that our solar system is not an isolated island, but rather a way station along the Milky Way, constantly welcoming visitors from the vast expanses between the stars. This posed an interesting question about the surge in September. Were we witnessing a random concentration of unrelated objects, or could there be deeper connections between FA-22 other near-Earth asteroids and the mysterious interstellar visitor that had dominated the astronomical headlines? Before we could answer that question, we needed to understand what else was sharing the cosmic stage during those remarkable autumn weeks. Part 3, Swan, Apophis, and a surging comet. While asteroid FA-22 captured the headlines with its close approach, another astronomical phenomenon was quietly preparing for its debut in the evening sky. Comet Swan was discovered by the Solar Wind Anisotropes instrument on the SOHO spacecraft on September 11th, and was rapidly brightening. It became visible to the naked eye as it plunged toward the sun. Unlike the predictable and well-charted orbit of FA-22, this comet represented something far more unpredictable and volatile. The discovery of the comet by Swan highlighted one of the most elegant aspects of modern astronomy. The space-based instrument was not designed to hunt comets. Its primary mission was to map hydrogen emissions from the interacting solar wind at the edge of our solar system. But it turns out that as comets begin their final approach toward the sun, they begin to release hydrogen-rich water vapor in quantities detectable from millions of kilometers away. Swan essentially stumbles upon new comets by tracking their hydrogen signatures as they flare up in interplanetary space. By mid-September 2025, GI had brightened to about magnitude 6, hovering right on the threshold of naked-eye visibility under a dark, rural sky. Amateur astronomers began reporting sightings near the constellation Virgo, near the bright star Spica, and the red glow of Mars in the western sky. After sunset, the comet's tail grew longer and more structured, as the sun's heat sublimated the volatile ice layers from its nucleus, creating the coma and the classic cometary tail that have inspired the human imagination for millennia. But comets are incredibly fragile creatures. Unlike the structure of solid rock and metal found in asteroids, comets are essentially loose, dirty snowballs, aggregations of ice, dust, and organic compounds held together by weak gravitational attraction and frozen volatiles. As they approach the sun, the very heat source that creates their magnificent tails can also tear them apart completely, Many comets discovered by Swan never survived their first close encounter, creating streams of material and brief meteor showers before disintegrating completely. The physics behind cometary activation involves the complex interplay of sublimation temperatures and solar heating. Water ice begins to sublimate at around 200 Kelvin, while more volatile compounds like carbon dioxide and methane begin to outgas at even greater distances from the Sun. As these materials turn directly from a solid to a gaseous state, they create jets of gas that can significantly alter the comet's trajectory through non-gravitational forces. This makes cometary orbits difficult to predict accurately, especially for objects making their first approach from the distant Oort cloud. The survival of C 2025 GI remained an unknown throughout September. New comets from the outer reaches of the solar system often contain pristine ice crystals that have never been exposed to significant solar heat. And when they finally encounter solar radiation, the rapid sublimation can create internal stresses that exceed the comet's structural integrity. The nucleus can break into multiple fragments, each creating its own tail and coma, or it could completely disintegrate into an expanding cloud of debris. However, even as this new comet captures the attention of amateur observers, another cosmic performer is preparing for its own moment on the stage. Asteroid 99,942 Apophis, the 400-meter-wide mountain of rock that once topped every list of concerns for planetary defense, continues its inevitable approach for its closest encounter in recorded human history. On April 13, 2029, Apophis will skim past Earth at a distance of just 32,000 kilometers, closer than even our geostationary communication satellites, close enough to appear as a fast-moving, bright star, visible to the naked eye even from urban areas. This flyby will occur at a speed of about 50 kilometers per hour, meaning that observers will be able to track the asteroid's movement against the background of stars in real time, without the need for a telescope. What makes the Apophis encounter so compelling, scientifically, is that we know for certain that it poses no impact risk for at least the next century. Radar observations and optical tracking have refined its orbit with extraordinary precision, eliminating the possibility of an impact during the 2029 flyby, or for many decades thereafter. This allows scientists to focus entirely on the remarkable opportunity to study a large asteroid during an extremely close approach. The gravitational effects from Earth's pull during the flyby will be profound and permanent. Apophis will experience tidal forces strong enough to alter its rotation speed, modify its surface features, and possibly trigger landslides or redistribute the regolith across its entire surface. The post-encounter asteroid will be measurably different from the asteroid before it, creating a natural laboratory for studying how close planetary encounters reshape small bodies over geologic time. NASA's OSIRIS-APEX mission, the extended mission of the successful OSIRIS-REx sample return spacecraft, is on its way to rendezvous with Apophis immediately after the 2029 flyby. The spacecraft will spend months mapping the asteroid's surface. After the encounter, taking measurements, how its gravitational interaction with Earth has changed its physical properties and internal structure. This data will be invaluable for future missions, for asteroid deflection, which must account for how the target objects react to external forces. The timing of Apophis's approach, just 3.5 years after the September 2025 swarm, raises interesting questions about whether we are entering a period of increased activity for near-Earth objects or not. Statistically, close asteroid approaches do not follow a specific schedule. They are essentially random events, governed by the complex gravitational interactions that have shaped the solar system over billions of years. However, the concentration of significant encounters in such a short period seems to challenge the notion of a completely random distribution. Part of this apparent increase stems from observational bias. The completion of major asteroid surveys like Linear, NEAT, and Spacewatch over the past 2 decades has dramatically improved our ability to detect and track potentially hazardous objects. The Vera C. Rubin Observatory, which captured its first light images in June 2025, represents another quantum leap in survey capability. Its massive field of view and sensitive detectors will rescan the entire observable sky every few nights, providing an unprecedented cadence for discovering new objects and tracking known ones. But improved detection capabilities alone do not explain the September surge or the incredible diversity of the objects involved, along with the close approach of FA-22 and the brightening display of C-2025 GI. Dozens of smaller near-Earth objects threaded their way through our local cosmic neighborhood, with Object 2025 GI passing just 0.78 lunar distances away on September 15th. Multiple approaches under 1 lunar distance occurred throughout the month, each one cataloged and tracked by the global network of space surveillance. The seasonal timing may offer a clue to the underlying dynamics. Earth's orbit moves us through different regions of the solar system, inside throughout the year, and perhaps September 2025 coincided with our passage through a particularly dense region of space debris, or this apparent concentration could be the result of complex gravitational resonances that can synchronize the orbits of multiple objects over geological timescales. Comets add another layer of complexity to this cosmic dance, unlike asteroids which follow relatively stable and predictable orbits. Comets can undergo dramatic orbital changes due to outgassing and gravitational perturbations. From the giant planets, long-period comets, from the Oort cloud, arrive with virtually no warning on trajectories that have not brought them into the inner solar system for thousands or millions of years. The distinction between asteroids, comets, and meteors is often a source of confusion in public discussions about planetary defense. However, these differences are crucial for understanding impact risks and mitigation strategies. Asteroids are essentially mountains of rock or metal in space, following well-defined orbits that change slowly over time. Comets are volatile, rich bodies whose behavior can be unpredictable. Due to outgassing effects, meteors are simply the phenomenon of light, made visible when small particles burn up in Earth's atmosphere. Regardless of whether their parent body is an asteroid or a comet, this diversity of small bodies reflects the complex history of the formation and evolution of our solar system. The asteroid belt between Mars and Jupiter contains remnants of planetary formation that never succeeded in forming a planet, while comets preserve pristine samples of ice and organic material from the distant reaches of the early solar nebula. Each population tells part of the story of how planets form around stars, and each poses different challenges for planetary defense. As the autumn of 2025 approaches, the cosmic stage is set for even more astonishing revelations. The familiar increase of objects in the solar system in September is about to be overshadowed by something unprecedented, a visitor from a completely different star system, carrying chemical signatures that would challenge the fundamental assumptions about planetary formation and the nature of interstellar space. But first, this mysterious visitor would have to navigate the gravitational environment of our complex inner solar system, while remaining hidden in the sun's glare. During its closest approach to the sun, when it would finally emerge into the view of telescopes in early December, Oumuamua would prove to be unlike anything astronomers had ever seen before. Part 4. The Interstellar Intruder, on July 1st, 2025. A routine automated sky survey captured something extraordinary. Hidden as an unremarkable pinprick of light, the Atlas telescope in Rio Negro, Chile, had captured thousands of similar objects. Asteroids, comets, and distant stars shifting position against the background of fixed stars. But this tiny dot would soon rewrite our understanding of what travels between the stars. Initially classified only as a potential near-Earth object, the object that would later be known as Atlas looked no different from the countless other discoveries in the Atlas database that the automated systems had flagged for follow-up observation, based on its apparent motion across the sky. And within a few days, telescopes around the world were tracking its trajectory with increasing precision. It was during this routine astronomical follow-up that astronomers realized they were dealing with something unprecedented. The calculations were unmistakable, as more observational data helped to refine the object's orbital elements. One parameter stood out with startling clarity. Its orbital eccentricity exceeded 1. In celestial mechanics, this is the telltale sign of a hyperbolic trajectory, a path carrying enough velocity to escape the sun's gravitational pull entirely. This object was not bound to our solar system. It was just passing through. Atlas became the interstellar visitor, confirmed as the third in human history, after the mysterious, cigar-shaped object, Oumuamua, in 2017, and the comet 2I Borisov in 2019. But unlike its predecessors, Atlas arrived at the perfect time for extensive observation. Its trajectory would bring it to perihelion, its closest point to the Sun around October 30th. 2025, followed by its closest approach to Earth, in December at a distance of about 1.8 astronomical units. That December distance is equivalent to about 270 million kilometers, far enough to pose absolutely no threat to Earth, but close enough to perform detailed spectral analysis using our most powerful telescopes. It was as if the universe had arranged a special gift, dropping a pristine sample from another star system, with optimal viewing conditions and plenty of advance notice. But the object's orbit was only the beginning of its mysteries. As observational data accumulated throughout the summer and early autumn of 2025, Atlas began to show characteristics that challenged assumptions about both interstellar space and cometary behavior. Size estimates from observations by the Hubble Space Telescope indicated an upper limit of about 5.6 kilometers for the nucleus, although the actual size could be significantly smaller. This placed it in an intermediate range between typical cometary nuclei and small asteroids. But what truly set Atlas apart from its interstellar predecessors was its unmistakable comet-like behavior. Unlike 1I Oumuamua, which showed no visible signs of a coma or tail, despite a puzzling non-gravitational acceleration, 2I Borisov developed a classic cometary appearance as it approached the Sun. By September, ground-based telescopes had resolved a substantial coma, the cloud of dust and gas surrounding the nucleus, along with the beginnings of what would become an impressive tail structure. This cometary activity provided the first clues about the object's truly alien chemical composition when the James Webb Space Telescope turned its infrared spectrograph toward Atlas in late summer of 2025. The results were unlike anything ever seen in solar system comets. The object's coma showed an unusually high ratio of carbon to water vapor. Among them, the highest ratio of CO2 to H2O ever measured in a comet. To understand why this chemistry is so significant, consider how comets form in planetary systems. Typically, with water condensing from the protoplanetary nebula at temperatures around 150 Kelvin, corresponding to an orbital distance of about 2 to 3 astronomical units from a sun-like star. Carbon dioxide with a lower sublimation temperature would condense much farther out beyond the snowline, where temperatures drop below 78 Kelvin. The extreme dominance of CO2 in Atlas suggests formation in the frigid outer regions of its parent planetary system, much farther out than where most solar system comets formed. Either this object condensed from an unusually carbon dioxide-rich protoplanetary disk, or it formed so far from its parent star that water ice never had the chance to accumulate in significant quantities. But the chemical anomalies did not stop with carbon dioxide. Spectral observations from the Very Large Telescope in Chile revealed another puzzling feature: prominent nickel emission lines with a surprisingly weak signature of iron. In typical solar system comets, iron and nickel appear in near-solar proportions, reflecting the composition of the stellar nebula from which they condensed. The apparent depletion of iron relative to nickel in Atlas suggests chemical processing or formation conditions, unlike anything in our cosmic neighborhood. As autumn progressed and Atlas continued its approach to perihelion, its tail structure became increasingly complex and spectacularly beautiful. The Gemini Observatory and other ground-based facilities captured multiple tail components, with different orientations and compositions, indicating the ongoing activation of volatiles across different regions of the nucleus. This object was truly coming alive under the sun's gaze, after perhaps billions of years in the cold void of interstellar space. The window for observing Atlas presented both opportunities and challenges as it neared perihelion in late October. The comet would become increasingly difficult to observe from Earth due to its proximity to the sun in our sky. The sun's glare would obscure the object during its period of most intense activity, when thermal processing might reveal more clues about its composition and internal structure, but patience would be rewarded. Earth's orbital motion would gradually improve the viewing geometry. Throughout November and into early December, Atlas would emerge from behind the sun's glare into a prime viewing position for its closest approach to Earth in mid-December, when the object would still be nearly 200 times farther away than the Moon, but was favorably positioned for major observatories to conduct extended spectroscopic campaigns. The months of observation held a tantalizing mystery. What changes would occur as Comet Atlas reached its peak solar heating? Would its unusual chemical composition remain stable? Or would the intense radiation drive off the surface materials, revealing different components underneath? Most importantly, would the object survive its perihelion passage intact? Or would the thermal stresses cause it to fragment into many pieces, like so many comets before it? Preliminary dynamical models suggested that Comet Atlas could be extremely ancient, possibly more than 7 billion years old, if recent calculations linking it to the galaxy's thick disk population proved correct. This would make it older than our entire solar system, a wanderer that had drifted through interstellar space before the Earth even existed. The preserved chemical signatures in its ices and rocky components could provide a direct sample of conditions in the early galaxy when the rate of star formation and the abundance of heavy elements were significantly different from today. Unlike the brief visit and rapid departure of Oumuamua, Comet Atlas offered the possibility of extended study over multiple observing seasons. Its moderate approach velocity and favorable geometry would keep it within reach of large telescopes until at least 2016, providing an unprecedented opportunity to characterize in detail a genuine object from another star system. But even as astronomers prepared for months of detailed observation, lingering questions remained about the object's origin and its journey to our solar system. How long had it wandered through interstellar space? What star system ejected it? And under what circumstances, most intriguingly, was its appearance? During the same time frame as the September asteroid surge, purely a coincidence? Or could there be deeper connections between the interstellar visitor and the unusual concentration of near-Earth objects? The apparent synchronization of cosmic events was beginning to strain credulity. First, the series of close-approaching asteroids, then the brightening comet, and finally, the arrival of an interstellar visitor with unprecedented chemical signatures. Either we were witnessing an extremely unlikely convergence of unrelated phenomena, or something more fundamental was orchestrating this celestial performance. The object, Atlas, continued its journey toward perihelion, hidden behind the ever-brightening glare of the sun. Astronomers could only speculate what discoveries awaited it in December, when it would re-emerge. But even then, this object had begun to reveal secrets that would reshape our understanding of planetary formation, interstellar chemistry, and our place in the galactic community. The question was no longer whether the visitor would offer new insights into the cosmos. The question was whether we were ready for the implications of what it might reveal about the universe beyond the boundaries of our solar system. The real mystery, however, was only just beginning to unfold. Because while the object Atlas captured the scientific community's attention with its alien chemistry and ancient origins, a growing number of researchers were beginning to recognize patterns in the September surge, suggesting something more than a cosmic coincidence was at play. Part 5. A Planetary Defense Wake-Up Call. The September surge of 2025 served as an uncomfortable reminder of how fragile our planetary defense capabilities still were, despite decades of technological advancement and international cooperation. Although we had successfully tracked and identified every significant object that approached Earth during those eventful weeks, the sheer succession of encounters highlighted vulnerabilities that could prove catastrophic if filled by the wrong kind of unwelcome visitor at the wrong time. Consider the fundamental challenge of detection geometry. The vast majority of our asteroid hunting telescopes are ground-based facilities, which can only observe objects when they are sufficiently far from the sun in our sky. This creates a significant blind spot in the direction of our nearest star, precisely the approach corridor that allowed the Chelyabinsk impactor to arrive completely undetected. In 2013, a meteor approaching from essentially the direction of the sun was invisible until the final hours or minutes before it entered the atmosphere. The orbit of FA-20, fortunately, carried it far from the blind spot. This detection allowed telescopes around the world to track its approach for several weeks before its closest approach. But if its orbit had been different, or if the vector of approach had been more aligned with the Sun-Earth line, we might have had only a few days or hours of warning, instead of the comfortable lead time that allowed for detailed characterization and public notification. This sunward blind spot represents one of the most significant weaknesses in our current planetary defense architecture. Ground-based surveys have made significant progress in cataloging near-Earth objects, but they are fundamentally limited by the laws of optics and orbital mechanics. You cannot observe what is hidden behind the brightest object in the sky. No matter how sophisticated your telescopes are, the solution involves placing detection systems into space, where they can operate independently of the Earth's day-night cycle and atmospheric interference. NASA's Near-Earth Object Surveyor mission, scheduled to launch in September 2027, will deploy an infrared space telescope specifically designed to hunt for asteroids from a position trailing Earth in our orbit around the Sun. From this vantage point, the NEO surveyor will be able to detect approaching objects from directions that are invisible to ground-based observatories. But space-based detection is only the first step in a complex chain of planetary defense capabilities. Once a potentially hazardous object is detected, it must be characterized in sufficient detail to assess its actual threat level and determine the most effective response strategy. This requires rapid follow-up observations from multiple facilities, precise orbit determination, and detailed analysis of the object's physical properties. The Vera C. Rubin Observatory is scheduled to capture its first light images in June 2025, representing a revolutionary step forward in this follow-up capability. Its giant mirror and wide-field camera can rescan the entire accessible sky every 3 nights, providing an unprecedented cadence in tracking newly discovered objects and monitoring their orbital evolution. In its first 10 hours of operation, Robin detected thousands of new asteroids, demonstrating the instrument's potential to significantly expand the catalog of near-Earth objects. However, detection and tracking are meaningless without the ability to actually do something about incoming threats. This is where NASA's Double Asteroid Redirection Test mission provided real-world confirmations. Invaluable for spacecraft kinetic impactor technology. DART impacted the asteroid Dimorphos on September 26, 2022, successfully changing the orbital period of this small asteroid by 32 minutes, far exceeding the minimum 4-minute change required. To confirm mission success, more importantly, detailed analysis of the impact revealed that the momentum transfer efficiency, known as beta, was approximately 3.6, meaning the impact was nearly 4 times more effective than predicted. By the simple law of conservation of momentum, this enhancement factor is a result of the post-impact ejecta plume, which acted like a rocket exhaust to amplify the deflection effect. Understanding this physics is crucial for designing future deflection missions. The European Space Agency's Hera mission is now on its way to the system and will arrive in 2026 to conduct a forensic analysis of the DART impact site. Hera's detailed mapping and measurement of the crater and ejecta will provide ground truth data for impact models, helping to refine our understanding of how different types of asteroids respond to kinetic deflection attempts. But a kinetic impactor is just one tool in the potential planetary defense toolkit for larger objects, or scenarios requiring more precise orbital changes. Other techniques might prove more effective. A gravity tractor, a spacecraft that uses its own gravitational field to gently tug an asteroid off course, accumulating velocity changes over many years or decades. Nuclear devices could vaporize surface material to create a powerful, rocket-like thrust. Ion beam shepherds could use a focused particle beam to gradually erode one side of an asteroid, creating a low, continuous thrust over a long period. The key takeaway from planetary defense research is that all of these techniques require significant preparation time to be effective. A gentle nudge applied many years, or decades in advance, can eliminate the need for emergency measures at the last minute. This is why early detection is so crucial, not because we need time to evacuate cities or build underground shelters, but because a gentle deflection becomes exponentially easier with early warning. The International Asteroid Warning Network was established to coordinate a global response to potential impact threats and conducted what could be considered a real-world drill during the 2022 FA approach. The asteroid's brief appearance on the European Space Agency's risk assessment list, followed by its disappearance from that list. Its removal after additional observations provided valuable experience in the delicate balance between informing the public and preventing panic. How do you inform the world about a potential asteroid threat without causing economic chaos or social unrest? How do you coordinate international response efforts when dealing with objects that could affect multiple countries? These questions have no easy answers. But the flyby of 2022 FA provided an opportunity to test communication protocols and decision-making processes with relatively low stakes. The drill revealed both strengths and weaknesses in our current approach. The rapid sharing of observational data among nations allowed for the quick refinement of 2022 FA's trajectory and its timely removal from the risk assessment list once the threat had been ruled out. But communication with the public remained inconsistent, with some media outlets sensationalizing the initial risk assessment, while others ignored the story entirely until the safe flyby was confirmed. Part of this communication challenge stems from the inherent uncertainty in initial trajectory determination. When an asteroid is first discovered, its orbit is poorly constrained due to limited observational data. The region of uncertainty, the range of possible trajectories consistent with existing measurements, could include both impact and near-miss scenarios. Only additional observations could narrow this uncertainty enough to make a firm prediction. This creates a fundamental tension in communication, waiting until the probability of impact drops to zero, which means potentially losing precious preparation time if the object is indeed on a collision course, but releasing the information, while significant uncertainty remains, risks causing unnecessary panic, or worse, public skepticism if the threat assessment changes, as better data becomes available. The September surge also highlighted remaining gaps in our detection capabilities. Despite recent advances, long-period comets from the outer solar system can still appear with relatively little warning as their highly elliptical orbits spend most of their time in distant regions where they remain undetectable. For example, comet Swift-Tuttle will not return to the inner solar system until the year 2126, but its nucleus is estimated to be 26 kilometers in diameter, large enough to cause global devastation if its orbit were to intersect Earth's path. Perhaps most concerning are the city-killer-sized objects in the 100 to 300-meter range, large enough to cause regional devastation, but small enough to remain difficult to spot until they are very close to Earth. Current surveys have cataloged most of the objects, larger than 1 kilometer, capable of global impacts, but the inventory of smaller asteroids that could pose a hazard remains incomplete. The September events also raised uncomfortable questions about our ability to handle multiple threats at once, while FA-22 dominated the headlines. Tens of smaller objects were simultaneously transiting our cosmic neighborhood of our own. If multiple city destroyer-sized asteroids were approaching simultaneously from different directions, would our tracking and characterization capabilities be overwhelmed? Could we execute deflection missions against multiple targets using current technology and resources? These scenarios remain hypothetical, but they underscore the importance of continued investment in planetary defense infrastructure, the completion of the Rubin Observatory Survey, the deployment of the NEO Surveyor, and the ongoing development of technologies. Deflection represents significant steps toward a truly robust planetary defense capability, but they also only represent the beginning of what will be a multi-generational effort to protect human civilization from cosmic impacts. The good news is that planetary defense is fundamentally a solvable problem. Unlike earthquakes, volcanic eruptions, or other natural disasters, asteroid impacts can be entirely prevented with sufficient early warning and the right technology. The physics of deflection is well understood. The necessary technologies are within our current capabilities, and the framework for international cooperation already exists. What we need now is the political will to sustain funding and support for these systems. Over the long periods between major impact threats, planetary defense is like insurance. It may seem unnecessary until you actually need it. The surge in September served as a valuable reminder that we live in a dynamic cosmic environment where impacts are not a matter of if, but when. However, as astronomers work to catalog and classify the parade of near-Earth objects during those eventful autumn weeks, another kind of mystery began to emerge from the observational data. The timing of the encounters, the clustering of orbits, and the incredible coincidence of an interstellar visitor arriving in the same narrow time frame was beginning to stretch the bounds of statistical probability. Were we witnessing an extremely unlikely convergence of unrelated events? Or was something more fundamental orchestrating this cosmic dance? Part 6. A natural cartographer of chaos, the human brain, is exquisitely designed to detect patterns, even when none exist. This evolutionary adaptation helped our ancestors spot predators hiding in the tall grass, and recognize seasonal changes, which meant the difference between feast and famine. But in the context of astronomical phenomena, this same pattern recognition system can lead us astray, finding connections and conspiracies in the random noise. of cosmic events. However, sometimes the patterns are real. Consider the timeline of asteroid 2025 FA20 as it swept past Earth. On September 18th, at a distance of 2.2 times the lunar distance, 3 days earlier, the smaller object, 2022, Rise passed by at a distance of just 0.718 times the lunar distance. During that same week, many other near-Earth objects passed through our cosmic neighborhood. Each object was catalogued and tracked by global surveillance networks. Comet 2022. GI brightened to the point of being visible to the naked eye in the evening sky and lurking in the background. The interstellar traveler and Atlas were approaching their October perihelion, after a journey that may have lasted for billions of years. Taken individually, none of these events were particularly noteworthy, as tens of asteroids pass within range, 0.5 astronomical units of Earth each month, at a steady rate. The orbital mechanics were set in motion billions of years ago. Comets regularly brighten and fade as they approach and recede in their solar orbits. Interstellar objects, though rare, are an expected, natural consequence of planetary formation and evolution around other stars. But the clustering of these events in such a narrow window of time begins to challenge simple explanations based on cosmic coincidence. What are the odds of an interstellar visitor arriving in the same month as a period of near-Earth object encounters? Anomalously, what is the probability of a comet, newly discovered, reaching peak brightness just as multiple asteroids are making close approaches? One hypothesis worth considering involves gravitational steering, the possibility that the passing comet Atlas, moving through the inner solar system, could somehow influence the orbits of smaller bodies. Large objects, or celestial bodies, can disturb the orbits of lesser bodies, potentially creating a stream of debris or an entourage effect, which could explain the cluster of encounters in September. However, physics argues strongly against this scenario, because Atlas, even with its maximum estimated size of about 6 kilometers, carries insufficient mass to have a gravitational influence on objects millions of kilometers away. Newton's inverse square law means the gravitational effect diminishes rapidly with distance, becoming negligible. Moreover, on the scales involved in the September encounters, the orbital elements of the various September visitors show no indication, evidence of a common origin or a shared dynamical history. FA22 follows a typical near-Earth object trajectory, with moderate eccentricity and inclination. The smaller asteroids discovered during the month should exhibit the full range of orbital characteristics expected from the near-Earth object population. None of them showed a hyperbolic trajectory that would indicate a recent gravitational interaction with an interstellar interloper. A more plausible explanation for the apparent clustering involves observational bias and detection cadence effects. The Vera Rubin Observatory just achieved first light in June 2025, significantly expanding our ability to detect and track small near-Earth objects. Improved survey coverage naturally leads to more discoveries, creating the impression of increased activity, even if the underlying population remains the same. Think of it like suddenly installing high-definition security cameras in an area that was previously unmonitored. The number of people passing through the space does not change, but your awareness of their presence increases dramatically. Similarly, advanced astronomical surveys reveal the true density of near-Earth objects, objects that were always there but simply went undetected by less sensitive instruments. The psychological phenomenon of pareidolia, the tendency to perceive meaningful patterns in random information, may also be influencing how we interpret the September events. Once the first few close approaches were reported, both astronomers and the public became hyper-aware of subsequent discoveries. Objects that might have been overlooked in a quieter news cycle suddenly made headlines, creating a feedback loop that amplified the perception of unusual activity. However, Even when accounting for observational biases and psychological effects, certain aspects of the September surge remain difficult to explain through purely random processes. The discovery of the Atlas star on July 1st, with its trajectory precisely calculated for maximum visibility, right at the time the near-Earth object activity peaked, represents an astonishing coincidence, pushing the boundaries of statistical probability. Consider a speculative alternative scenario. What if the Atlas star was not a single object, but the largest member of a dispersed cluster of interstellar material? If the original parent body had fragmented during its long journey through space, perhaps due to internal stress or collisions with interstellar dust, the resulting debris stream could spread out over a significant volume of space. In this scenario, the September asteroid encounters could represent smaller fragments of the same original object, following slightly different orbits, bringing them close to Earth at different times. The fragments would retain their interstellar velocity characteristics, but might have been gravitationally captured into temporary orbits around the Sun during previous passages through the inner solar system. However, this fragmentation hypothesis faces significant observational challenges. Spectral analysis of the September asteroids reveals a typical carbonaceous or silicate composition, consistent with an ancient solar system origin. Their reflectivity, where measured, matches known asteroid classification classes, rather than the unusual chemistry displayed by Atlas. If these objects shared a common origin, we would expect to see similar chemical signatures across the entire population. Furthermore, the orbital dynamics do not support a common origin scenario. True interstellar fragments would display hyperbolic orbits, similar to Atlas, not the elliptical orbits, characteristic of gravitationally bound solar system objects. The energy requirement to capture interstellar object fragments into stable near-Earth object orbits exceeds what is available through gravitational interactions with the planets. Perhaps the most mundane explanation is also the most likely. We are witnessing the statistical equivalent of multiple lightning strikes, individually unlikely events that occasionally cluster together through sheer chance. The universe is under no obligation to distribute cosmic encounters evenly across human timescales. Random processes can and do create apparent patterns that seem meaningful to a pattern-seeking intelligence. The rapid expansion of survey capabilities in the mid-2010s means we are observing this region of space with unprecedented sensitivity and frequency. Many generations of astronomers might have missed most of the September encounters entirely, or detected them as individual events spread across different news cycles. Our current ability to discover, track, and characterize multiple near-Earth objects at once creates an opportunity for a sharp focus that did not exist in previous eras of astronomical observation. However, even if rational analysis suggests that this is a coincidence and observational bias, a lingering sense of orchestrated timing remains. The precise arrival of Comet Atlas during a period of heightened activity by near-Earth objects, combined with its unprecedented chemical signatures and its ancient origins, suggests that we may be witnessing something more significant than a random convergence of unrelated events. The answer may not emerge until we have had several months to study Comet Atlas in detail, after it re-emerges from the Sun's glare in December. Detailed spectral analysis, precise orbital measurements, and careful comparisons with the September asteroid population might reveal connections that are not apparent in preliminary observations. But if no such connections emerge, if Comet Atlas proves to be entirely separate from the September encounters, then we are left with an even more fascinating possibility. Perhaps the universe is simply more dynamic and interconnected than our typically Earth-centric view can usually perceive. Perhaps what seems like an extraordinary convergence from our limited perspective is actually business as usual on a galactic scale. The question isn't whether something is following Atlas. The question is whether we are finally developing the observational capacity to perceive the true complexity of the cosmic environment we have always inhabited. And if so, then the September surge may be just the beginning of our education in what it means to be citizens of a galaxy, where 400 billion stars constantly exchange material across vast interstellar space. But before we can answer those larger questions, we need to understand why Comet Atlas itself is behaving so strangely. Because as the autumn progressed and the interstellar visitor drew closer to the Sun, telescopes around the world were documenting its activity and chemical signature, unlike anything ever seen in comets before, either in our solar system or anywhere else. Part 7. Strange Behaviors and Unusual Characteristics. As Comet Atlas continued its approach to perihelion in October, telescopes around the world began to record behaviors that challenged the fundamental principles and assumptions of physics, as well as interstellar chemistry. What initially seemed like a relatively straightforward case of a wandering comet from another star system revealed layers of complexity that seemed to violate the rules established for how such objects behave. The most notable anomaly emerged from observations by the Webb Space Telescope, conducted throughout August and September of 2025. The JWST's infrared spectrometer detected an unprecedented level of carbon dioxide as the primary component of the comet's coma, with a CO2-to-water ratio among the highest ever measured in any comet. This was not just unusual, it was nearly impossible according to conventional models of cometary formation and evolution. To understand why this chemical composition is so astonishing, consider how comets typically form in planetary systems from water condensing out of protoplanetary disks at temperatures around 150 Kelvin, which corresponds to an orbital distance of 23 astronomical units from Sun-like stars. This is why most comets in our solar system, which formed in the outer regions beyond Neptune's orbit, still contain a significant amount of water ice, mixed with other volatiles, carbon dioxide, with its much lower condensation temperature, only becomes a major cometary component at distances exceeding 10 astronomical units from the parent star, where temperatures drop below 80 Kelvin. Even then, CO2 typically remains a minor component compared to water ice. The extreme dominance of carbon dioxide in Atlas suggests it formed under conditions different from anything in our solar system, or that subsequent processing depleted its water selectively while preserving the CO2. One possibility involves formation in the frigid outer regions of a much larger or colder planetary system than our own. If Atlas condensed from a protoplanetary disk around a star of low mass, or in the distant reaches of a system with many gas giants, it could have formed in a region where carbon dioxide ice is the primary volatile component in such environments. Water may have never condensed in significant quantities, leading to the extreme compositional ratios observed by the JWST. Alternatively, the object might have undergone intensive processing during its long journey through interstellar space. Cosmic ray bombardment over millions or billions of years could have altered its surface chemistry. Through radiolysis, the breaking of chemical bonds by high-energy radiation. If this process preferentially removed water molecules while leaving carbon dioxide intact, that could explain the current composition without requiring special formation conditions. But the chemical anomalies did not stop with the dominance of carbon dioxide. Spectroscopic observations from the Very Large Telescope in Chile revealed another puzzling feature: prominent emission lines from nickel atoms with corresponding signatures, surprisingly weak from iron, which represents a significant departure from the typical composition of the solar system, where iron and nickel appear in ratios roughly equivalent to the elemental abundances of the stellar nebula, from which they condensed. The marked depletion of iron relative to nickel in Atlas raises fundamental questions about its formation environment or its subsequent evolution. One possible hypothesis involves the differential processing of metallic components during the object's interstellar journey. Iron and nickel have different sublimation temperatures and chemical reactivities, so prolonged exposure to cosmic radiation or collisions with interstellar dust may have selectively removed iron, while preserving nickel in a more stable chemical form. Another intriguing possibility relates to the chance that Atlas formed in a stellar environment with a non-solar elemental abundance. If its parent star belonged to a different galactic population, perhaps the thick disk or the halo, which contained stars with unusual chemical compositions, then the resulting planetary debris might naturally exhibit an iron-to-nickel ratio different from what we see in our own cosmic neighborhood. As summer turned to autumn and the comet flew on, Atlas approached its perihelion in October, its tail structure growing increasingly complex and visually spectacular. In ground-based observations from facilities like the Gemini Observatory have recorded multiple tail components with different orientations, varying colors and particle sizes. This multi-component structure suggests the sequential activation of different volatile substances from various regions of the nucleus. The physics behind this complex tail development involves the sublimation of different types of ice as the comet encounters increasing solar heat. As carbon dioxide begins to outgas at much greater distances than water, ice, it likely creates an initial coma and tail dominated by carbon dioxide. As the object moves closer to its perihelion, water ice can trigger a second phase of tail development with different optical properties and dynamic behaviors, polarimetry measurements, which analyze the polarization state of scattered sunlight from the coma and tail, have provided further clues about the nature of the dust particles ejected from the nucleus. The polarization signature suggests that the dust particles have an unusual size distribution, or optical properties compared to typical solar system comets. This could indicate different formation processes in their original protoplanetary disk, or extensive alteration during their long journey between the stars. A particularly fascinating aspect of Comet Atlas's behavior was its sudden brightenings, which seemed to occur independently of its distance from the Sun. Most comets follow predictable brightening curves as they approach perihelion, with their brightness increasing steadily as their distance from the Sun decreases. But Comet Atlas showed more complex internal processes. These outbursts could be caused by the sudden exposure of volatile rich material. When the surface crust is removed by solar heating, many comets develop an insulating mantle of processed dust and organics, which prevents sublimation, until thermal stresses or gas pressure fracture these protective layers. When a breakthrough occurs, the pristine ice underneath can sublimate rapidly, creating a sudden and temporary surge in activity, or this intermittent behavior could reflect internal structural changes as the ice layers adjust to solar warming. After billions of years, perhaps in the cold void of interstellar space, why a temperature differential penetrating deep into the nucleus could cause subsurface sublimation, fracturing the internal ice layers and exposing new surfaces to solar radiation, and creating chain reaction events. The rotational axis of Bi-Atlas also appeared unusual, compared to typical comets in our solar system. Photometric observations designed to measure brightness variations as the nucleus rotates revealed one of two possibilities: an unusually long rotation period, or a complex tumbling motion that made determining a period difficult. This could indicate structural changes during its interstellar journey, or simply reflect its initial angular momentum state from whatever event ejected it from its parent star system. But perhaps the most perplexing aspect of Bi-Atlas's behavior was how normal it seemed. In some respects, while being completely unprecedented in others, the fundamental physics of coma formation, tail development, and the sublimation of volatiles followed principles that were well understood. However, its specific chemical signatures, temporal evolution, and structural properties seemed to violate every expectation. based on decades of cometary research. This combination of familiar and alien characteristics suggested that bi-Atlas represented something truly new in astronomical experience, not just another comet from another star system, but a window into planetary formation processes and stellar environments, fundamentally different from our own cosmic neighborhood. The object simultaneously confirmed and challenged our understanding of how planetary systems evolve and what kinds of debris they can eject into the galaxy. As bi-Atlas approached its final weeks, before passing perihelion and temporarily disappearing behind the sun's glare, the accumulating observational evidence painted a picture of an object that defied easy classification. It was clearly a comet, based on its activity and spectral characteristics, yet its chemical composition and behavioral patterns did not align with any known class of object in our solar system. The question became, did these anomalies reflect genuinely exotic physics and chemistry, or simply represents an extreme of natural variation among the debris of planetary systems? And that question will have to wait, to be resolved until December, when Atlas will emerge from its hiding place behind the sun and give telescopes their best chance to analyze its characteristics in detail. But even as astronomers prepared for months of intensive observation, another kind of speculation had begun to emerge from the data. Because, while the strange behavior of Atlas could be explained through processes that were bizarre but natural, they also raised uncomfortable questions about whether we were dealing with something more than just an unusually active comet from another star system, alien technology, or a natural wonder. In an age of social media and viral conspiracy theories, it was perhaps inevitable that Atlas would eventually face the question that has haunted every unusual astronomical discovery since the dawn of the space age. Is this evidence of extraterrestrial intelligence, the object's unprecedented chemistry, its complex behavior, and the incredible timing of its observation, sent conspiracy theorists into overdrive? In late September of 2025, the speculation was initially quite harmless within academic circles, where researchers noted similarities between Atlas and the controversial object Oumuamua, which had sparked debates about a possible artificial origin back in 2017. Both were interstellar travelers. Both exhibited unusual properties that challenged conventional understanding, and both arrived on trajectories that offered excellent observation opportunities for human astronomers. But the similarities mostly ended there, and the differences were profound and telling. Unlike Oumuamua with its mysterious cigar-like shape and enigmatic non-gravitational acceleration without any visible outgassing, Atlas behaved exactly like the comet it appeared to be, developing a classic coma and tail. As it approached the sun, its brightness varied in patterns, predictable based on volatile sublimation. Its orbit showed the gravitational deviations expected from its interaction with the sun, with additional disturbances easily explained by the force of outgassing. Most importantly, Atlas showed no signs of controlled or directed movement. Its path through the solar system followed a hyperbolic trajectory, precisely as expected for an unbound object, subject only to solar gravity, with no course corrections, no anomalous acceleration, no radio transmissions, no visible geometric shape or artificial structure, even under the highest resolution observations from humanity's telescopes. The scientific method requires extraordinary evidence for claims. The extraordinary data and evidence regarding Atlas always point to natural phenomena, albeit natural phenomena unlike anything ever observed in our cosmic neighborhood. Every strange behavior, every unusual chemical signature, every anomalous physical property has plausible explanations rooted in well-established physics and chemistry. Consider the extreme dominance of carbon dioxide that made Atlas's chemistry so remarkable. Though unprecedented among comets in the solar system, This composition could easily be the result of formation in the outer regions of an unusual planetary system. Stars of different masses, metallicities, or planetary architectures could naturally produce comets with chemical signatures that seem alien to observers accustomed only to the products of our local solar system. The apparent depletion of iron relative to nickel, while puzzling, might reflect formation in a stellar environment with non-solar elemental ratios, or subsequent processing over billions of years of travel between the stars, cosmic ray bombardment, interstellar dust impacts, and thermal cycling in the cold depths of space could alter the surface composition selectively in ways that produce unusual spectral signatures, and without requiring any artificial intervention. Even the complex tail structure, multiple components, and the sudden brightening events have precedence in solar system comets, admittedly to an extreme degree, regarding the observed behaviors. Comet Hale-Bopp displayed multiple tail components with different compositions, and Comet Holmes experienced a dramatic outburst, increasing its brightness by nearly 1,000,000 times in 2007. Natural processes are clearly capable of producing the spectacular displays and unusual behaviors observed in Atlas. The real question is not whether Atlas could be artificial, but why people keep asking. Part of the answer lies in the profound psychological impact of contemplating the truly interstellar scale. When we observe objects from other star systems, we are confronted with the possibility that intelligence may exist elsewhere in the galaxy. The human mind, evolved to navigate social hierarchies and detect agency in complex environments, naturally seeks signs of purpose or intent in unexplained phenomena. This tendency becomes even more potent when dealing with objects that seem to violate our expectations or exhibit properties that go beyond the limits of conventional explanation. The unusual trajectory and favorable observational geometry of Oumuamua triggered the same pattern recognition systems that our ancestors used to identify potential predators or allies. When faced with something unprecedented, the brain often defaults to the assumption that someone or something must be responsible. But nature frequently creates phenomena that go far beyond human imagination. The universe has had 13.8 billion years to experiment with physics and chemistry under conditions ranging from inside giant stars to the near absolute zero temperatures of interstellar space. The fact that we occasionally encounter natural processes or objects that surprise us is not evidence of an artificial origin. It is evidence that our understanding of cosmic phenomena is still fundamentally incomplete. The media landscape surrounding astronomical discoveries also tends to amplify speculation about artificial origins. Headlines like, "Scientists perplexed by mysterious interstellar visitor," generate more clicks than researchers study an unusual but natural comet, regardless of which headline more accurately reflects the scientific consensus. This creates a feedback loop where public interest drives sensational coverage, and this in turn fuels more speculation about exotic explanations. Social media exacerbates this effect by allowing unverified speculation to spread faster than careful scientific analysis. By the time astronomers have gathered sufficient data to characterize an object and rule out an artificial origin, alternative theories have already spread widely and become resistant to factual correction. The historical pattern is clear and consistent. Every unusual astronomical discovery, from pulsars to fast radio bursts, has initially faced speculation about its origin, being possibly artificial in every case. Continued observation and analysis have revealed natural explanations, which, while often more complex and fascinating than initially expected, do not require the intervention of extraterrestrial intelligence. This does not mean we should abandon the search for evidence. Regarding extraterrestrial technology, the universe almost certainly contains other intelligent civilizations, and some of them may be capable of interstellar travel or communication, but the detection of such civilizations would require clear, unambiguous evidence of an artificial origin, coherent radio signals containing information, objects exhibiting controlled motion, inconsistent with natural forces, or structures that violate the laws of physics as we understand them. Atlas exhibited none of these characteristics. Its radio emissions, where detected, consisted entirely of natural thermal radiation and molecular emission lines typical of gas outgassing from a comet. Its trajectory followed gravitational mechanics, predictable with perturbations, easily explained by the sublimation of volatile, its internal structure, as revealed by thermal modeling and photometric observations, was consistent with ice and rock held together by gravity and weak cohesive forces. Perhaps most telling, Atlas behaved exactly as we would expect. From the debris of planet formation around other stars, theoretical models predict that every star system ejects a significant number of small bodies during its early formation and evolution. These objects would then wander through interstellar space for millions or billions of years before occasionally encountering other star systems, where they might be observed as interstellar visitors. The chemistry and physics of such objects should reflect the conditions in their parent systems, different stellar masses, different elemental compositions, different planetary configurations, different thermal histories. A true sample of debris from another star system would look unfamiliar compared to objects in our solar system, but would still obey the fundamental laws of physics and chemistry that govern matter in the universe. In other words, Atlas looks exactly like what it appears to be, a natural product of planetary system formation around another star, carrying the chemical signatures that reflect different formation conditions from those that produced our own solar system. The fact that it seems strange to an observer is not evidence of an artificial origin, but rather a confirmation that we live in a galaxy where the conditions for planet formation vary considerably between systems. As the comet, Atlas continues to near its point of closest approach, the accumulating evidence continues to support natural explanations for its unusual properties. But that raises a question, even more fascinating than whether it is artificial. It is the question of what, precisely, this wandering object has experienced over the billions of years of its formation and its recent appearance in our cosmic vicinity. The answer to that question will require sophisticated modeling of galactic dynamics and the motion of stars over geological timescales. But initial efforts to trace the trajectory of Atlas backward through space and time have begun, to yield fascinating clues about the object's origin and its remarkable journey that brought it to our telescopes at just the right time for detailed study. Part 9. The Origin and Biography of Atlas. Tracing the biography of an interstellar visitor requires reconstructing a journey that may have lasted longer than the lifetime of Earth itself. Atlas carries within it chemical and orbital signatures, fossil records of cosmic events that took place billions of years ago when our galaxy was young, and the distribution of stars and heavy elements was significantly different from the configuration we see today. The first clues about the object's ancient origins emerge from kinematic analysis, mathematical models that attempt to trace its motion backward through space and time. Preliminary calculations by researchers at the European Southern Observatory suggest that Atlas may have originated from the galaxy's thick disk. Stellar population formed during the early evolution of the Milky Way 7 to 12 billion years ago. If these kinematic models prove to be correct, Atlas would be older than our entire solar system. It would have been wandering through the space between stars long before the sun condensed from its parent molecular cloud, carrying chemical signatures from an era when the rate of star formation was higher and the galaxy's abundance of heavy elements was different, significantly, from what it is today. The thick disk hypothesis receives support from the object's unusual chemical composition. Stars in this ancient component of the galaxy typically exhibit different patterns of elemental abundance. Compared to younger thin disk populations like our Sun, the apparent iron depletion and extremely high carbon dioxide content observed by Atlas may reflect formation around a thick disk star, with a non-solar metallicity and an unusual volatile chemistry. But how does a small body escape its parent planet in its star system and begin its long journey through interstellar space? The ejection process often involves gravitational interactions with giant planets. During the chaotic early stages of planetary system evolution, as giant worlds migrate inward or outward due to interactions with protoplanetary disk material, they can scatter smaller bodies onto hyperbolic orbits, sending them out of the system entirely. Computer simulations suggest that every planetary system ejects a vast amount of debris during its formation. For every 1 kilogram of material that remains gravitationally bound to its planets, asteroids, and comets, perhaps 10 kilograms are flung into interstellar space by the gravitational slingshot effect. This means that the galaxy is filled with trillions of wandering fragments from billions of stellar nurseries. A vast exodus of planet-building debris adrift between the stars, once ejected from its parent system, by Atlas would have begun a solitary journey through the near vacuum of space between the stars. The typical density of matter in interstellar space is about 1 atom per cubic centimeter, better than anything achievable in laboratories on Earth. In this environment, the object was essentially isolated from external influences, preserved in the deep freeze of the cosmos, at a temperature just a few degrees above absolute zero. However, this interstellar journey was not entirely uneventful modeling. Recently conducted by galactic dynamics experts has identified multiple close approaches to other star systems during Atlas's long voyage. In the last 10 million years alone, the object appears to have passed within 1 parsec, about 3 light-years, of at least half a dozen different stars. Each approach would have likely altered its trajectory through subtle gravitational perturbations. Most significant among these later encounters occurred about 4 million years ago, when by Atlas passed within a range of about 1 light-year of a red dwarf in the constellation Cassiopeia. The gravitational pull from this close encounter was enough to significantly alter the object's trajectory, potentially explaining why its current motion is not directed toward any obvious parent system within the population of the galaxy's thick disk. This raises fascinating questions about the object's surface evolution during its interstellar journey. Bombardment by cosmic rays over millions of years would have gradually altered its surface chemistry, with exposed ice and rock undergoing nuclear decay and fission reactions. High-energy particles from distant supernovae and other galactic phenomena would have broken chemical bonds, creating strange isotopic ratios, and possibly forming entirely new molecular species not found in typical solar system material. The extreme cold of interstellar space, typically around 3 Kelvin, would have preserved most volatile materials in solid form throughout the journey. But periodic encounters with interstellar dust clouds or the radiation fields of nearby stars could have caused episodic heating events, possibly sublimating surface layers and redepositing them in different configurations. This might explain some of the unusual chemical signatures observed by modern telescopes. Perhaps, most remarkably, Atlas has maintained its structural integrity throughout its billion-year journey, despite enduring temperature shifts, cosmic ray bombardment, and occasional impacts with interstellar dust particles. This suggests either an incredibly durable structure or capacity for continuous self-repair, where sublimation and redeposition gradually heal damage from micrometeoroids and radiation-induced structural changes. The object's arrival in our solar system marks the culmination of a journey almost beyond human comprehension. Consider the temporal precision. By Atlas needed to arrive at the right time and trajectory for optimal observation by our 21st century telescopes. This object had to survive for billions of years in the harsh environment of interstellar space, navigate the gravitational influences of dozens of stellar encounters, and arrive during the brief historical moment when humanity possesses the technological capability to see it, to recognize and study it. This timing seems too perfect to be a coincidence. Atlas approached perihelion just as our most advanced space telescopes were operational and our understanding of interstellar chemistry had become sophisticated enough to appreciate its significance. A few centuries ago, it would have been dismissed as just another faint star, and a few centuries from now it might have been detected, but not properly characterized before disappearing back into the cosmic depths. The story of Atlas also illuminates the larger narrative of galactic evolution and the cosmic recycling of planetary material. Every heavy element in the object's composition was forged in the nuclear furnaces of ancient stars and scattered across space by supernova explosions. The carbon, oxygen, silicon, and trace metals that make up its structure represent the alchemical accumulation of countless generations of stars. Stars that lived and died long before this solar system ever existed. In a very real sense, Atlas acts as a messenger from the ancient galaxy, carrying with it samples of planetary formation that occurred under significantly different conditions than those that produced the Earth and its companions. The object's chemical composition provides direct evidence of how volatile materials condense and evolve in the environments of stars with different metallicities and dynamic histories. But perhaps the most profound aspect of Atlas's biography is what it reveals about the interconnectedness of galactic-scale processes. This object began its existence as part of a planetary disk forming around another star, perhaps in a completely different region of the galaxy. Through a complex chain of gravitational interactions, stellar motions, and cosmic accidents, it eventually found its way to our telescopes, carrying information about its origins. Across vast distances and timescales, the thick disk origin hypothesis, if confirmed, would make Atlas a fossil from the youth of the Milky Way, a time when the galaxy was more actively forming stars, and the chemical composition of interstellar space was significantly different from today's values. Studying this ancient, wayward object could provide detailed insights into the chemical evolution of the galaxy, both early planetary formation and the distribution of materials, volatile materials in the primordial galaxy. However, despite all the sophisticated modeling and chemical analysis, the origin of Atlas remains unresolved. We cannot definitively identify its parent star or the planetary system where it formed. The gravitational chaos of galactic evolution has erased most traces of its original orbit, leaving only statistical hints of a possible origin from the thick disk. This uncertainty reflects the inherent challenges of interstellar archaeology. Unlike terrestrial fossils, which remain embedded in datable rock layers, interstellar travelers like Atlas carry no direct evidence of when or where they originated. Their stories must be reconstructed through indirect clues, chemical composition, isotopic ratios, orbital analysis, and statistical models of galactic dynamics. But these limitations do not diminish the significance of what Atlas represents. Even without knowing its exact birthplace, we can be confident that it carries authentic samples from another world, formed under conditions different from those in our own solar system. Every observation, spectrum, and chemical analysis provides new data on the diversity of planet formation processes and the range of environments where worlds can emerge around other stars. As Atlas continues its final approach to perihelion in late October of 2025, astronomers are preparing for the object's temporary disappearance behind the sun's glare, The weeks immediately following perihelion will be the most scientifically valuable phase of the entire encounter, as the maximum solar heating will drive the highest levels of outgassing and potentially reveal subsurface materials that have been preserved since the object's formation billions of years ago. But the sun's glare will hide Atlas during this most active phase, adding an element of suspense to the unfolding story. Will the object survive its perihelion passage intact, or will the thermal stress cause it to fragment into multiple pieces like so many comets before it? When it re-emerges into telescopic view in December, will it still exhibit its unusual chemical properties and complex patterns of activity, made it remarkable throughout its unanswered approach? The answers to these questions would have to wait. But in the meantime, the September surge and the incredible characteristics of Atlas raised unsettling possibilities about the nature of our cosmic neighborhood and humanity's place within it. Were we witnessing a random convergence of unrelated phenomena, or could there be deeper patterns at play connecting the interstellar visitor? With the unusual concentration of near-Earth objects, some researchers began to wonder whether the September events were merely a coincidence or the prelude to something grander. A cosmic drama unfolding on a scale that could dwarf human understanding of celestial mechanics and galactic evolution. Part 10. Spectacular Hypotheses, Cosmic Dominoes. The human imagination, when faced with phenomena that transcend our everyday experience, tends to conjure extraordinary explanations. In the case of Atlas and the September event, speculations began to surface about possible chain reactions. The idea that an interstellar visitor could somehow trigger a cascade of cosmic events that could fundamentally alter the dynamics of the solar system. Could Atlas have gravitationally stirred up the asteroids, like a cosmic spoon mixing ingredients in a celestial soup? No, the math definitively refutes this romantic notion. Even at its maximum estimated mass, a few trillion kilograms, Atlas would be a mere minnow, gravitationally speaking. In the vast ocean of solar system dynamics, its influence on near-Earth objects at distances of millions of kilometers would be utterly negligible compared to the gravitational dominance of the overwhelming sun and the planets. Newton's inverse square law is relentless in its mathematical precision. The gravitational effect diminishing with the square of the distance means that Atlas's ability to influence other objects drops to essentially zero at the scales involved in the September encounters. To put this in context, the gravitational pull between Atlas and asteroid FP22 during their simultaneous presence in the inner solar system would be roughly equivalent to the gravitational attraction between two parked cars in neighboring cities. However, the persistence of these compelling theories reveals something important about human psychology and our relationship with cosmic phenomena. We instinctively search for causal relationships between simultaneous events, even when physics makes such connections impossible. This tendency helped our ancestors in identifying cause and effect in their terrestrial environment, but it can lead us astray when applied to astronomical phenomena that operate on scales far grander than human experience. More speculative scenarios involve possible connections between comet Atlas and solar activity, where an interstellar visitor could trigger increased solar flares or coronal mass ejections, which could affect space weather around Earth. This idea touches upon legitimate concerns about the interaction between the Sun and the Earth, as well as the vulnerability of our modern technological civilization to geomagnetic storms. However, the physics of solar dynamics operates on energy scales that make the interaction between a comet and the Sun fundamentally insignificant. The Sun releases approximately 3.8 times 10 to the power of 26 watts of energy continuously, more in a single second than human civilization has consumed throughout its entire recorded history. The gravitational and electromagnetic influence of a small, extrasolar comet at a distance of over 100 million kilometers would be utterly overwhelmed by the far greater forces driving solar variability. Solar activity follows well-documented cycles related to the sun's internal magnetic dynamo, not the presence or absence of tiny visitors on the outskirts of the solar system. Correlations between comet appearances and solar events do sometimes occur by pure chance, but these coincidences represent statistical noise rather than a causal relationship. The meteor shower scenario presents another intriguing, but ultimately unfounded speculation, suggesting that Comet Atlas might be trailing a cloud of debris that could create spectacular meteor showers as Earth passes through the material. This idea seems plausible on the surface, because many annual meteor showers is the result of the Earth encountering streams of debris left behind by comets. But interstellar meteor streams face fundamental physical problems, making them essentially undetectable from Earth. The debris ejected from Atlas carries the same hyperbolic velocity as its parent body, meaning that any particle it sheds will also escape the solar system rather than entering stable orbits that could intersect Earth's path. By the time our planet reaches the region where Atlas passed through, any ejected material would have dispersed throughout vast volumes of space, to the point where the particle density becomes negligible. Furthermore, the high relative velocities in interstellar encounters mean that any debris that did somehow collide with Earth would impact our atmosphere at speeds exceeding 70 kilometers per second, much faster than typical meteors within the solar system, which would produce brilliant, brief flashes of light, rather than the long-lasting streaks characteristic of regular meteor showers. The fragmentation hypothesis represents another attempt to find a hidden link between Atlas and the September asteroid encounters, suggesting that Phi 22 and other near-Earth objects might be fragments of the interstellar visitor that broke apart during a previous passage through the inner solar system and are now following independent orbits, bringing them back into Earth's vicinity. This scenario faces issues that are insurmountable in terms of orbital mechanics and chemical composition. True fragments from Atlas would retain its hyperbolic orbit and interstellar chemistry, similar to the parent body. The September asteroids exhibit neither of these characteristics. Their elliptical orbits and composition of typical carbon or silicon suggest a conventional solar system origin, with no connection to interstellar matter. Perhaps the most persistent speculation about the chain of events involves conspiracy theories. The idea that government agencies might be concealing evidence of more dramatic effects or discoveries related to Atlas. This theory touches upon legitimate concerns about transparency in space surveillance and the possibility of military implications, kept top secret from asteroid detection capabilities. However, the reality of modern astronomical practice strongly refutes any large-scale cover-up scenario. A global network of professional and amateur astronomers operates on the principles of open data, the rapid sharing and publication of discoveries. Major observatories publish public observation schedules and target lists, and the orbital elements of objects newly discovered appear in international databases within days of confirmation. The incentive structure of academic astronomy also works against secrecy, as career advancement depends on publishing significant discoveries in peer-reviewed journals and presenting results at international conferences. A conspiracy to hide information about Comet Atlas would require coordination among thousands of researchers across dozens of countries, a logistical impossibility given the competitive nature of scientific research. More importantly, there is absolutely no credible evidence of hidden phenomena or secret discoveries related to Comet Atlas. Every aspect of the object's chemical and orbital behaviors consistent with natural phenomena, albeit natural phenomena, at the extreme end of previously observed ranges. However, even as rational analysis dismisses the more spectacular doomsday scenarios. A what-if scenario does merit our serious consideration. This is the possibility that we are entering an era in which the detection of interstellar objects increases dramatically. The unprecedented survey capabilities of the Vera C. Rubin Observatory, combined with improvements to space-based infrared telescopes and enhanced international coordination, could reveal that objects like Comet Atlas are far more common than once suspected. Current estimates suggest the Oort cloud and similar structures around other stars should eject about one interstellar object per year, detectable from Earth, with existing survey capabilities, but these estimates carry immense uncertainties, based on limited observational data from only 3 confirmed interstellar visitors. If the actual rate is higher, perhaps 10 or 20 interstellar objects might be detectable by the 2020s. Each year could witness a revolution in our understanding of the galactic scale exchange of material, rather than simply having interstellar visitors, are rare cosmic oddities. We might discover that our solar system is constantly showered with debris from thousands of other planetary systems. This scenario would transform interstellar archaeology from a speculative science, based on individual anomalous objects, into a systematic field of survey, capable of characterizing the chemical and physical properties of planet formation throughout the galaxy. We could begin to map the distribution of volatile materials in planetary architectures by studying the streams of debris that carry samples from distant worlds directly to our telescopes. Such a discovery would perhaps represent the most profound shift in our cosmic perspective since the Copernican revolution. Instead of viewing Earth and its fellow planets in our solar system as isolated products of local stellar evolution, we would recognize ourselves as participants in a galaxy-wide ecosystem, where matter constantly flows between star systems, across immense distances and timescales. The September outburst, seen from this perspective, might represent not an unusual concentration of unrelated events, but rather our first glimpse of the true level of activity in our cosmic neighborhood. As our detection capabilities improve and survey ranges expand, what currently seems anomalous may prove to be the normal state of affairs for a galaxy containing 400 billion stars, constantly exchanging debris through gravitational interactions and interstellar encounters. But before we can assess these grander implications, we must get through the immediate test of BA Atlas at perihelion and its re-emergence from the sun's glare. The object's behavior during its closest approach to the sun will provide crucial data on the resilience of interstellar comets and the preservation of ancient chemical signatures under extreme thermal processing. The stakes are higher than mere scientific curiosity. If BA Atlas disintegrates during its perihelion passage, we could miss the opportunity to study pristine interstellar material for many decades, or centuries until another similar visitor appears, with favorable observation conditions. But if it survives, its reappearance in December could provide the most detailed characterization of material from beyond the solar system ever achieved by human science. Part 11. The late 2025 to 2026 observation window. A cosmic dance in late 2025. Late 2025 is witnessing the culmination of a cosmic dance, as Comet B Atlas approaches its fateful date with the Sun. The 30th of October is marked as its calculated perihelion, the moment this ancient wanderer will make its closest pass to the Sun, after a journey that may have spanned longer than the existence of Earth itself. However, this crucial encounter will unfold beyond human sight, obscured by the overwhelming glare of our nearest star. For astronomers worldwide, the perihelion period represents both the most scientifically valuable phase of the entire encounter and the most difficult observational challenge. This is when maximum solar heating will drive the sublimation of volatile materials to its peak. potentially exposing subsurface materials, preserved since the body's formation billions of years ago, compounds that remained locked in a solid state throughout the long interstellar journey, will finally transition into a gaseous state, revealing their spectral signatures to any capable telescope. But the solar radiation, which promises to unlock Comet B Atlas's deepest secrets, also renders it nearly invisible from Earth. The body's trajectory has brought it to a distance of 0.414 astronomical units from the Sun, equivalent to about 66 million kilometers, closer than Mercury's orbital distance from Earth's perspective. This places Comet B Atlas less than 10 degrees from the solar disk, lost in the twilight glow, making astronomical observation nearly impossible. This forced observational hiatus has created a compelling mystery. Will Comet B Atlas survive its perihelion passage intact, emerging in December as a single body with enhanced activity due to the exposure of fresh volatiles? Or will the thermal stress fracture its internal structure, shattering it into multiple pieces and creating an expanding cloud of debris, observable as separate comets? The question of its survival carries far-reaching implications. As a matter of academic curiosity, surviving intact would demonstrate that interstellar objects possess sufficient structural integrity to preserve ancient chemical signatures, even when subjected to intense solar heating, fragmentation, while potentially creating a spectacular sight, could scatter the very materials that make the comet Atlas scientifically valuable, turning a pristine sample from another star system into a collection of processed debris streams. Historical precedent offers little guidance. Most comets in the solar system that disintegrate during a close solar approach are first-time visitors from the Oort cloud, experiencing significant solar radiation after millions of years in cosmic deep freeze. In contrast, Comet Atlas is a seasoned veteran that has demonstrated remarkable structural stability throughout its billion-year journey through interstellar space. The cosmic irony is palpable that after traveling unfathomable distances across space and time to reach our solar system, Comet Atlas will experience its most active and revealing moments while hidden behind the very star driving its spectacular transformation. This is like attending a concert, where the main performer disappears behind a curtain during their most important act. But the patience of astronomers is well rewarded. Earth's orbital motion around the Sun gradually improves the observational geometry. For objects passing close to our star, by early December, Comet Atlas will begin to emerge from the Sun's glare into a prime viewing position. The object is calculated to make its closest approach to Earth in mid-December, at a distance of about 1.8 astronomical units, equivalent to 270 million kilometers. This distance may seem vast by terrestrial standards, but it provides optimal conditions for detailed spectroscopic analysis, being close enough for large telescopes to gather a significant amount of light, yet far enough to avoid atmospheric interference from Earth's thermal radiation, and positioned in the pre-dawn sky, where background contamination will be minimal. The observation window in December will likely be the best opportunity for human science to study pristine interstellar material that it may encounter for many decades or centuries to come. Unlike Oumuamua's brief visit, the trajectory of Comet Atlas will keep it within the view of major observatories until 2026, providing many months of continuous observation across multiple wavelength bands. Meanwhile, other members of September's cosmic cast are preparing for their own moments of observation after being spotted brightening throughout the autumn, facing their own survival challenge as they approach perihelion in early November. New comets from the outer solar system often fragment under the sun's heat, but if this one survives, it promises to provide an opportunity for observation that is excellent for naked-eye viewing for observers in the northern hemisphere. The viewing window for the comet is narrowing as its orbit carries it deeper into the evening twilight. but experienced comet hunters have reported making naked-eye detections under dark, rural skies. Binoculars reveal its characteristic bright green core and a developing tail structure, pointing away from the sun, which are classic signs of vigorous sublimation activity. Whether this display will continue or end in the catastrophic fragmentation remains to be seen. Asteroid 99,940. Apophis continues its relentless approach for an encounter in April of 2029 that will bring it closer to Earth than our geostationary satellites. And although that is still more than 3.5 years away, ground-based observatories have already begun extensive characterization campaigns designed to map the asteroid's surface properties, rotational state, and internal structure before the close flyby alters these characteristics. NASA's OSIRIS-APEX spacecraft is on its way to a rendezvous with Apophis after an encounter with Earth, having conducted routine checkouts and necessary course adjustments during its multi-year cruise phase. The spacecraft will approach the asteroid in June of 2029, providing up-close observations of how the gravitational interaction with Earth has altered the asteroid's physical properties. But the most impressive upgrade to our space surveillance capabilities is still ramping up its operations. The Vera-C Rubin telescope has produced its first images, demonstrating an unprecedented ability to detect and track near-Earth objects. This facility is still in its commissioning phase in autumn 2025, and when operating at full capacity, Rubin will rescan the entire accessible sky in just a few nights, providing near real-time monitoring of the cosmic flow in our cosmic neighborhood. This enhanced frequency will revolutionize the detection and tracking of asteroids, potentially revealing that the September surge was not an unusual cluster but a pattern representative of the true level of activity in near-Earth space. Previous surveys, operating with much longer intervals between observations, may have missed many objects or failed to recognize clustering patterns that will become apparent under continuous monitoring. The space-based component of the detection network is also preparing for major upgrades. NASA's Near-Earth Object Surveyor, or NEO Surveyor, scheduled for launch in September 2027, will deploy an infrared telescope specifically optimized to detect asteroids from a position trailing Earth in its solar orbit. NEO Surveyor will be able to detect objects approaching from the direction of the Sun, which remain invisible to ground-based surveys. This capability will finally close the detection gap that allowed the Chelyabinsk meteor to arrive completely unnoticed in 2013. It's operational. NEO Surveyor will provide early warnings of incoming objects, regardless of their direction of approach, eliminating the solar blind spot, the greatest weakness in our planetary defense system. For amateur astronomers and citizen scientists, the latter part of 2025 offered many opportunities to make meaningful contributions to ongoing studies. Comet Quan remained within reach of small telescopes and even sophisticated cameras, allowing dedicated observers to document changes in its tail structure, brightness variations, and potential fragmentation. The reappearance of Comet Atlas in December will initially favor observers in the southern hemisphere, but its rapid movement across the sky will eventually bring it into view for observers in the northern hemisphere. Although the comet will be too faint for observation with the naked eye without significant telescopic assistance, it will be a target for experienced observers and astrophotographers could capture images showing the cometary structure and the development of its tail. More importantly, the coordinated observation of these diverse celestial bodies has provided valuable experience in international scientific cooperation and data sharing. The techniques and procedures developed to track Comet Atlas and characterize the September outburst will be directly applicable to defense scenarios for the planet in the future involving potentially hazardous asteroids. With a short warning time, the observational challenges in late 2025 also highlighted the importance of redundancy and international cooperation in astronomical surveys. No single telescope or survey system can provide complete coverage for all possible approach vectors and types of celestial bodies. Only through coordination between ground-based and space-based facilities across multiple wavelengths and observation cycles can we achieve a comprehensive awareness of our cosmic surroundings. As autumn gradually turns to winter and Comet Atlas prepares for its hidden solar encounter, the global astronomical community has mobilized resources for what could prove to be the most in-depth characterization of interstellar material ever undertaken. What is at stake extends far beyond academic curiosity. The data obtained during the October observation window could provide critical insights into planet formation, galactic chemical evolution, and the frequency of material exchange between star systems via interstellar objects. But first, Comet Atlas must survive its rendezvous with our star. The answer to that question will remain hidden until October, when telescopes around the world will turn toward the pre-dawn sky to discover if the ancient chemistry from another star system has survived the ultimate test on its billion-year journey to human science. Part 12. Envisioning the Future: Scenarios and Speculative Paths. The convergence of enhanced detection capabilities, improved redirection technology, and growing international cooperation in the late 2020s has set the stage for many possible futures in humanity's relationship with cosmic threats. The September surge and the cometary encounter, Atlas, shows us what these futures might look like, from successfully mastering our cosmic environment to sobering reminders of our vulnerability. In the most optimistic scenario, the technological and institutional foundations laid in the 2020s evolve into a robust planetary defense ecosystem, effectively eliminating the threat of asteroid impacts, while revolutionizing our understanding of the broader galactic environment. The unprecedented survey capabilities of the Vera C. Rubin Observatory combined with the infrared detection capabilities of the space-based NEO Surveyor and similar systems create a comprehensive awareness of incoming objects, with warning times of decades or even centuries. This extended lead time shifts asteroid deflection away from last-minute interventions into routine cosmic traffic management. Gentle nudges applied years in advance divert the paths of potentially hazardous objects onto safe trajectories using kinetic impactor techniques, proven and refined through multiple DART-style missions. This process becomes so reliable and predictable that asteroid deflection becomes on par with earthquake forecasting and hurricane tracking as accepted tools for natural disaster mitigation. Under this scenario, Comet Swan survives its 2025 perihelion and provides a spectacular naked-eye sight throughout the Northern Hemisphere's winter, inspiring a new generation of amateur astronomers and science enthusiasts. Comet Atlas escapes its solar encounter intact and delivers unprecedented insights into interstellar chemistry and galactic material exchange processes. The detailed characterization of Comet Atlas establishes interstellar archaeology as a major scientific field. Improved survey systems detect dozens of additional interstellar visitors throughout the late 2020s, with each visitor carrying unique chemical signatures of planet formation around other stars. By the early 2030s, the systematic comparison of interstellar debris will provide the first comprehensive survey of planetary chemistry across different galactic environments. This breakthrough science drives technological development in spectroscopy, precision astrometry, and coordinated multi-telescope observations. These capabilities prove invaluable for characterizing potentially hazardous asteroids, enabling the precise determination of structural composition and clear deflection requirements before any real threat materializes. International collaboration flourishes under the pressure of shared cosmic challenges. Procedures developed to coordinate observations of Comet Atlas evolve into standardized protocols for handling any unusual or suspicious celestial objects. Regular drills and training programs maintain readiness, while building global confidence and response capabilities. Public engagement in astronomy and space science reaches unprecedented levels as people around the world follow the unfolding discoveries and characterization efforts. Educational initiatives leverage this interest to improve scientific literacy and rational decision-making skills across diverse audiences. The combination of real cosmic threats and effective technological responses provides compelling evidence of the value of scientific research and international cooperation. While some scenarios are moderate, alternative ones present more difficult possibilities. The moderate path acknowledges that improved detection and deflection capabilities will face real-world tests as the catalog of potentially hazardous objects expands. Current surveys have identified most of the kilometer-sized asteroids capable of causing a global catastrophe, but the inventory of city-killer-sized objects in the 100 to 300-meter range remains incomplete. Statistical projections suggest that one or more objects in this size range will eventually approach Earth, without sufficient warning time to implement gentle deflection measures. These scenarios will demand more aggressive intervention techniques, potentially including nuclear explosive devices, which carry significant technical and political risks. For the first time, such an encounter might involve an object detected only months or weeks before a potential impact, forcing rapid decision-making about deflection strategies under immense time pressure and public scrutiny. Success would validate the investments in planetary defense and perhaps would spur expanded funding for detection and deflection capabilities. Failure could lead to regional damage, devastation, and fundamental questions about humanity's ability to protect itself from cosmic threats. Even partial success scenarios carry significant implications. A successful deflection effort that averts a global catastrophe, but does not eliminate all impact risk, could scatter debris across populated areas, creating multiple smaller impact sites instead of a single large crater. Public perception of such outcomes could shift from viewing planetary defense as a heroic safeguard to seeing it as a dangerous interference with natural processes. The challenge of ocean impacts. An impact over an ocean poses particularly complex challenges for both deflection strategy and public communication. The vast majority of the Earth's surface is covered by water, making an ocean impact more likely, statistically, than a land impact from a random asteroid strike. However, tsunami generation from undersea impacts is not perfectly understood, with significant uncertainties in current modeling efforts. A 200-meter-wide asteroid impacting deep ocean could generate 10-meter-high waves, potentially posing a hazard across an entire ocean basin, as coastal cities from Boston to Barcelona could face devastating tsunami impacts hours after a mid-Atlantic impact. The warning time provided by a successful detection might be sufficient for evacuation efforts, but the economic and social disruption would be immense even with no direct casualties. These scenarios underscore the importance of communicating accurate risks and realistic public expectations. Current planetary defense technology can handle most threats, given sufficient warning time, but late detection scenarios or unusually large objects could overwhelm deflection capabilities. Worst-case scenarios exist, which, though statistically unlikely, within a human lifetime, represent existential challenges that current technology cannot effectively address. A long-period comet from the Oort cloud could arrive with only a few months or years of warning, carrying enough kinetic energy to threaten human civilization, regardless of deflection efforts. Such bodies, with diameters potentially exceeding 10 kilometers, would require deflection energy, far beyond anything available through kinetic impactor techniques. Nuclear explosive deflection is theoretically possible, but the necessary technology development, international coordination, and deployment time could easily exceed the available warning time. These extreme scenarios remind us that planetary defense provides protection against most threats, but not all threats, much like earthquake-resistant building codes or hurricane tracking systems. Defensive measures can significantly mitigate risk without eliminating it entirely. The goal is not perfect security, an impossible standard, but rather reasonable protection against probable threats. Psychological and social factors, crowd psychology, and social dynamics introduce additional complexities in any scenario. Public reaction to asteroid threats depends heavily on risk communication strategies, media portrayal, and the level of trust placed in scientific and governmental institutions. Accurate information delivered by trusted sources can maintain social stability during crisis situations. Sensationalist reporting or conspiracy theories can undermine response effectiveness, even if technical capabilities are adequate. The September surge provided valuable experience in managing public communications about cosmic threats, but real impact scenarios would involve much higher stakes and more intense media scrutiny. Social media's amplification of both accurate information and misinformation can significantly complicate crisis management efforts. Economic and industrial impacts. The economic repercussions also vary significantly between different scenarios. Successfully repelling a major threat could generate significant public support for continued investment. Regarding planetary defense capabilities, failed or partially successful interventions could trigger more cautious approaches, emphasizing evacuation and damage mitigation over proactive deflection efforts. The increasing involvement of the commercial space industry and asteroid-related activities introduces market dynamics that could support or hinder planetary defense efforts, as private companies driven by the profits of asteroid mining might develop characterization capabilities and access with dual purposes for both resource extraction and deflection missions. But commercial priorities do not always align with the needs of planetary defense. A potentially hazardous asteroid that also contains valuable resources could face competing claims from mining companies and deflection missions. These conflicts would require careful legal frameworks to balance commercial interests with public safety requirements. International political challenges. International politics are perhaps the most unpredictable factor in future planetary defense scenarios. Current cooperative mechanisms work well during routine operations, but crisis situations involving potential impacts could trigger more competitive national responses. Nations might pursue independent deflection efforts rather than coordinating through international frameworks, leading to conflicting or counterproductive interventions. Technological trajectories and global challenges. The trajectory of technological development will also influence the most likely scenarios. Breakthroughs in fusion, propulsion systems, artificial intelligence, or materials science could significantly expand deflection capabilities and extend effective warning times. Conversely, budget cuts for space-based detection systems could leave us vulnerable to threats that current projections assume we will be prepared to handle. Climate change and other global challenges compete for the same financial and political resources needed for planetary defense investments. Public and governmental attention has limited bandwidth, and the threat from asteroids can seem abstract, or distant concerns might be given a lower priority than more urgent issues, such as economic inequality, environmental degradation, or international conflict, a cosmic perspective and human cooperation. However, the cosmic perspective that celestial bodies like Comet, Atlas provide creates unique opportunities to overcome divisions on Earth and focus on the common good of humanity. The knowledge that our planet exists within a dynamic galactic environment, filled with potential threats and opportunities, can foster cooperation in ways that purely terrestrial challenges cannot achieve. As we stand on the threshold of advancements that could be revolutionary in our ability to monitor and manage cosmic threats, the future that unfolds will depend as much on our social and political choices as on our technological capabilities. The September event and the encounter with Comet Atlas serve as both an inspiration and a warning of what lies ahead in humanity's relationship with the wider cosmic environment. But before any long-term scenarios can play out, we must first learn what Comet Atlas will reveal as it re-emerges from its hiding place in the sun's glare. In December, the spectral signatures and physical properties recorded during that critical time could give us our first detailed look at pristine material from another star system, and for the first time, we might truly understand what it means to be citizens of a galaxy where worlds continually exchange their most precious assets across the vast distances between stars. Part 13. A Cosmic Conclusion. As winter settles over the northern hemisphere, and Comet Atlas prepares for its reappearance in December, emerging from the sun's bright glare, we find ourselves at a remarkable turning point in humanity's relationship with the cosmos. The events of September 2015, from the close approach of FA-22 to the brilliant performance of Comet Swan, to the discovery of our third confirmed interstellar visitor, have offered us something far more valuable than scientific data or the validation of planetary defense. They have given us a new lens through which to see our place in the cosmos, shifting a perspective held for most of human history. The night sky seems silent and predictable, with the stars wheeling overhead in eternal patterns. The 9 planets wander along their predestined orbits, and occasionally a comet or meteor brings brief reminders that space is not entirely empty. This perspective fostered a sense of cosmic isolation, where Earth and its inhabitants seemed to be the unique products of local stellar processes, fundamentally separated from the rest of the galaxy by unimaginable distances and timescales. But September 15, 2002, shattered this illusion of isolation. We discovered that our solar system is not a quiet suburban neighborhood on the outskirts of cosmic activity, but rather a bustling crossroads, where ancient travelers from distant worlds frequently pass through, carrying messages from their origins. By Atlas, in particular, represented a direct physical connection to the stellar processes that occurred billions of years ago in regions of the galaxy we may never be able to visit by spacecraft. This represented not just a scientific discovery, but a fundamental shift in our cosmic perspective, comparable to the Copernican revolution or the discovery of the expanding universe. We are not the isolated products of a single star system, but participants in galactic-scale processes, where the exchange of matter and information between worlds has occurred for longer than the Earth has existed, its chemical signatures preserved in the specimen. This ancient meteorite carries information about the rate of stellar nucleosynthesis, planetary formation conditions, and the volatile chemistry in the environment that existed before our sun began to shine, with each spectral observation providing a direct sampling of the processes that shaped the galaxy in its infancy, when the rate of star formation was higher and the distribution of heavy elements was significantly different from its configuration today. But perhaps most importantly, the September events demonstrated that we now have the technological capability to recognize, study, and potentially interact with this system of material exchange on a galactic scale. The same detection networks that tracked the approach of FA-22 and will monitor the Apophis flyby in 2029 can also identify and characterize interstellar visitors like by Atlas, with precision sufficient to extract scientific information. In detail, we have evolved from passive observers of cosmic phenomena to active participants in interstellar archaeology, every new survey telescope commissioned, every refined spectroscopic technique, every international cooperation agreement signed, brings us closer to a comprehensive understanding of our galactic neighborhood and our place within it. This transformation carries profound implications that extend far beyond astronomy and planetary defense. The infrastructure necessary for monitoring cosmic threats and studying interstellar visitors, precise detection systems, rapid response capabilities, and international coordination mechanisms provide models for addressing other global challenges that transcend national borders. Climate change, pandemic response, resource management, and environmental protection all require a similar combination of scientific understanding, technological capability, and international cooperation. The lessons learned from tracking asteroids and characterizing comets could prove equally valuable for monitoring greenhouse gas concentrations, predicting disease outbreaks, or managing our shared oceans and atmospheric resources. More fundamentally, the cosmic perspective nurtured by the awareness of visitors, like the Interstellar by Atlas, offers an antidote to the narrow-minded thinking that often hinders cooperation on global issues. When we realize that Earth exists within a dynamic galactic ecosystem, where matter constantly moves between star systems across vast distances and timescales, the divisions on Earth based on nationality, ideology, or economic systems begin to seem less significant. We are all passengers on the same tiny planet, weaving its way through the galaxy, filled with ancient fragments from billions of other worlds. The carbon atoms in our bodies were forged in the furnaces of stars that died before our sun was born. The water we drink may have come from comets from outside the solar system. The air we breathe contains elements that have traveled between the stars for longer than complex life has existed on Earth. This understanding transforms environmental protection and social cooperation from abstract moral imperatives into the practical necessities for becoming cosmic citizens. We cannot squander the rare and precious conditions that allow complex chemistry and evolution for biology to flourish on the surface of our planet. Nor can we fragment our ability to respond due to short-sighted competition when faced with challenges on a galactic scale. The September surge also highlighted what we still do not know about our cosmic neighborhood and the processes that govern it. Current models predict that objects interstellar would be relatively rare, perhaps one detectable object every few years, under optimal observation conditions. But if Atlas represents a typical level of activity rather than an exception, our estimates could be off by orders of magnitude. The Vera C. Rubin Observatory and other next-generation survey systems may reveal that tens or even hundreds of objects interstellar pass through the solar system annually, most of them too small or too faint to be detected with current technology. This would change our understanding of the rate of galactic material exchange and the frequency of information transfer between star systems. Such discoveries would also raise profound questions about the prevalence of complex chemistry and possibly biological processes throughout the galaxy. If interstellar space is filled with organic compounds and volatile materials originating from diverse planetary environments, then the building blocks of life may be far more widely distributed than we currently realize. Every comet that enters the solar system, whether from the local Oort cloud or from distant interstellar space, carries with it samples of the chemical conditions that existed during its formation. These natural laboratories provide direct access to processes and environments far beyond the reach of even the most ambitious spacecraft missions. But harnessing this research potential requires continued investment in the detection, tracking, and analysis capabilities that made the September discoveries possible. The technologies and institutional frameworks that allowed us to identify Oumuamua as an interstellar visitor and to track its journey represent decades of scientific development and international cooperation. These capabilities are not self-sustaining. They require continuous funding, technological upgrades and political support from governments and organizations around the world. The long intervals between major impact threats or spectacular interstellar visitors might tempt people to cut back on investment in planetary defense and space surveillance systems. This would be a grave mistake. The September outburst has shown us that our cosmic neighborhood is far more dynamic and interconnected than we ever thought. We are finally developing the observational tools and analysis necessary to understand our place within the galaxy-scale processes that have been unfolding for billions of years. The coming decades could witness revolutionary advances in our understanding of planetary formation, stellar evolution, and the chemical evolution of the galaxy, based on the direct sampling of interstellar materials delivered to our telescopes through natural cosmic processes, but only if we maintain and expand the capabilities that made these discoveries possible. The choice before us is clear. We can embrace our role as cosmic citizens, investing in the knowledge and institutions necessary to monitor and understand our galactic environment, while safeguarding our planet from cosmic threats. Or we can retreat into terrestrial short-sightedness, abandoning our cosmic perspective, just as we are beginning to glimpse the true complexity and wonder of the universe that we inhabit. The September outburst and the encounter with Comet Atlas argue powerfully for the first choice. We have been given unprecedented opportunities to study pristine samples from other star systems, while demonstrating our growing ability to protect Earth from cosmic threats. These achievements represent the beginning of humanity's transition from a purely planetary species to one that actively participates in galactic-scale phenomena. But this transition will only succeed if we maintain the curiosity, collaboration, and commitment to scientific inquiry that made it possible. The universe has delivered incredible gifts to our telescopes and our detection networks. Whether we prove worthy of these gifts will depend on the choices we make in the coming months and years. Atlas is preparing to reappear from behind the brilliant glare of the sun, carrying chemical signatures from another star system and another era of galactic evolution. We are ready to receive the messages about the process of planet formation and the exchange of cosmic material that we cannot study in any other way. What we learn from this ancient wanderer could reshape our understanding of how worlds form around other stars, how materials essential for life are distributed throughout the galaxy, and the true meaning of being cosmic citizens. In a universe where 400 billion stars continuously exchange the most precious substances across the vast distances of interstellar space, the September outburst is just the beginning of the real adventure in cosmic archaeology. And interstellar understanding lies ahead, waiting for us to develop the wisdom and cooperation necessary to read the messages that ancient wanderers, like Atlas, carry through the dark voids between worlds.